So let's go ahead and quantify our entropy changes. So once again, let's think about what's happening. We have our system and we have our surroundings. Before we were talking about the heat, right? If the heat leaves the system, so it's exothermic, the heat is going to the surroundings. So if our heat leaves our system, that same amount of heat is being gained by the surroundings. So our Q of our surroundings, Q is heat, right, is equal to the negative Q of our system. Therefore, we can quantify our entropy of our surroundings by saying they are equal to negative Q of the system, right? Because Q of the surroundings is equal to negative Q of the system. Normally, it would not give us our Q of our surroundings, so we would need to solve for negative Q of our system. Or they gave us Q of our system, we can solve for that by solving Q of our surroundings. So our delta S of our surroundings is equal to negative Q of our system divided by our temperature. The one thing, though, is that we need to make sure we are at constant pressure and temperature. Normally, you would not see this. I'm not going to give you any problems where you'll have a change in pressure or temperature. So therefore, if those are constant, we know that our Q is equal to our H, our delta H, our enthalpy. We did that last semester. So our delta S of our surroundings equals negative delta H of our system divided by our temperature. Our temperature needs to be in Kelvin. And remember, there is no change in temperature here. So if we consider the combustion of propane gas, so here's the expression, the equation, right? They gave us delta H of the reaction. Let's think real quick. What's our system? What's our surroundings? So our system is going to be our reaction, right? What's actually happening. So this is technically delta H of our system is negative 2044 kilojoules. Okay. The surroundings then would be everything else around it. So you're standing out by the campfire, right? You're part of the surroundings. So is the air around it. The system is just this combustion reaction. So it wants us to calculate the entropy change in the surroundings associated with this reaction, the sign of the entropy change of the system, and the sign of the entropy change of the universe. Is this reaction spontaneous? So A, the entropy change of the surroundings. So what we need to do is, well, let's take a look. What did it tell us? Delta H of our surroundings is equal to negative delta H of our system divided by our temperature. So they gave us delta H of our system, right? Did they give us a temperature? Yeah, they did, 25 degrees Celsius. So we can take our temperature. We need to change that to Kelvin. So 273 plus 25 is 298 Kelvin. We can plug it in our equation. So delta S of our surroundings equals negative, right? Because we're looking for our surroundings. So it's negative delta H of our reaction or delta H of our system. So it's going to be negative of negative 2044 kilojoules divided by our temperature in Kelvin. So we end up getting 6.86 kilojoules per Kelvin. Normally we would put this in joules, so that's why they did the conversion to joules. So our delta S of our surroundings is positive. So do we have an increase in entropy of our surroundings? Now it wants us to determine the sign of the entropy change of the system. So let's look at our system. Here's our system, right? We have gas molecules, so all of these are gas. So which is more spontaneous? Well, over here on the left, we have 6 moles of gas, right? We got 1 mole of propane and 5 moles of oxygen. So we got 6 moles of gas going to 7 moles of gas. So which is more spontaneous? It looks like the reaction is going to occur to the right. So our delta S of our system is going to be positive. So we have a positive delta S. We have a positive delta S of system and surroundings. So overall, what is the sign of the entropy change of the universe? Well, looks like this is positive plus that. It is going to also be positive. or delta S of our universe is positive, and therefore our reaction is spontaneous. Go ahead and pause, try this example. There are the answers, so make sure you got the answers right. So let's take a look at our temperature dependence on our delta S of our surroundings. So surroundings are everything outside of what we have. So if we add heat to the surroundings that are cool, so your surroundings are cold and you're adding heat, it has more effect on the entropy than if the surroundings were already hot. So if we added heat to surroundings that were hot, it wouldn't make much difference, right? But if our surroundings were cool and we added heat, it would make much difference. So let's think about water. Water freezes below 0 degrees Celsius. We know that, right? That's spontaneous. Because heat is released on the freezing, so we know if something's getting colder, right, it's releasing heat. That means there is an increase in entropy of our surroundings. The surroundings, it has to be high enough that our delta S is positive. So let's take a look at what that means. So over here, we are at low temperatures. So at a low temperature, that means that our system, right, we know our system is getting more ordered, isn't it? It's going from a liquid to a solid when it freezes. So our entropy is always going to decrease no matter what. If we're at a low temperature, our delta S of our system is going to decrease. If we're at a high temperature, our delta S of our system is going to decrease. It's always going to decrease when we are going from a liquid to a solid. But what about our surroundings? So if we're at a low temperature, right, it's going to give off a lot of heat. And so our system gives off that heat to our surroundings. So our surroundings are able to increase its entropy. Overall, then, when we add a negative and positive together, right, we get our delta S of our universe, in this case, is positive. So that is why this is a spontaneous process at low temperatures. If we were at a high temperature, though, there would not be much change in our delta S of our surroundings. And therefore, the difference between these two, our delta S of our universe, would end up being negative. So above 0 degrees Celsius, the entropy increase of our surroundings is not high enough that our entropy would end up being positive of our universe. And so that's why above 0 degrees Celsius, water does not freeze. It does not have to do technically with temperature, right? It really, in the end, all has to do with the entropy. This is crazy, guys. This is something you hadn't thought about before, right? You just knew at 0 degrees Celsius, water froze. The reason water freezes below 0 is because our delta S of our surroundings, it gives off enough heat that our delta S of our universe is positive, and thus we are able to have water freeze at low temperatures. At high temperatures, it is not spontaneous just because we don't have enough energy for it to freeze. It's not spontaneous. So when our entropy change of our universe is unfavorable, so our universe is unfavorable, right? It's negative. The entropy change of the surroundings must be positive and large to make the overall universe positive. So we always have to have, remember, delta S of our universe always has to be 0 or positive. So if our delta S of our system is negative, our delta S of our surroundings needs to be larger in order to make this a positive number. So then we end up talking about the energy of the system, our Gibbs free energy. This will help us determine whether something is spontaneous or not. It's a little bit easier to use than just our delta H or delta S, okay? These compare delta S and delta H. So a process will be spontaneous when delta G is negative. So before we said if delta H is negative, it would be exothermic, right? If delta S is negative, then it would be non-spontaneous, right? we might need to make a little chart about all of these different values. So delta G will be negative if delta H is negative and delta S is positive. Therefore, it is exothermic, right? Because delta H is negative, and our delta S is going to be positive, meaning that we have a more random system. So therefore, our delta G will be negative, meaning that it is spontaneous. If our delta H is negative and very large, okay, so that means it's exothermic, but our delta S is negative, so that means it's not random, but it's very small, we can still have a delta G that's negative, meaning it's spontaneous. So there are different conditions, right, based upon our values. So normally, if our delta G is positive, meaning that it's not spontaneous, that means that normally we would have a positive delta H, right, meaning that it's not spontaneous, and a positive delta S, a negative delta S, meaning that it's not spontaneous. So you do have to keep these delta H's, delta S's figured out, which ones are which, in order to determine what we know about delta G. So if delta G is negative overall, it will be spontaneous. If delta G equals 0, then our reaction's at equilibrium, and we don't need to worry about it. So here's our entropy change of our universe. So here's some reaction, okay? We got nitrogen, right, plus hydrogen gas. So over here, there is a lot of free energy, right? Because we look, let's see, on the left, we have 4 moles of gas. So we have a lot of free energy on the left. On the right, we have ammonia, right? So we got some pure ammonia over here. What's going to happen is, in order to reach equilibrium, right, we're going to make more moles of our ammonia. So it'll be spontaneous going down to equilibrium. This one, the ammonia, will also be spontaneous going to equilibrium until we have a mixture of these gases. So here we actually have more moles of gas, don't we? Because we have a mixture of all of these. So that we can compare our Q to our K, and we can figure out what is spontaneous. So when we have high energy, as you can see, look at this energy diagram. When we are at higher energy, so in the beginning we're at a high energy, in the end we're at a high energy, then that means that it is going to be spontaneous, right? As we decrease our energy, well, this is not spontaneous. This equilibrium does not want to automatically go back to just pure ammonia or just pure nitrogen and hydrogen. So when you have high free energy, it is spontaneous. When we are at equilibrium, our delta G is equal to 0. So our Gibbs free energy. Here is our equation for Gibbs free energy. Our negative T delta S of our universe equals our delta H of our system minus our T delta S. So our Gibbs free energy is the maximum amount of work energy that can be released to the surroundings by a system for a constant temperature and pressure system. So that's what this means over here, okay? This is our delta G. We sometimes call this the chemical potential because it is related to how much energy we can store in a mechanical system. So our delta G of our system equals negative H of our system minus T delta S of our system. So at any point in time, we can figure out what's going on. What is our delta G value? Because our delta S of our universe determines if it is spontaneous, that means delta G also determines if it's spontaneous. So if delta S of our universe is positive when it's spontaneous, which we know is true, right? Delta S of our universe is positive, then our delta G will be negative. So here are some examples, and I'll get that in a second.